So because we are unable to solve this problem analytically, let me now just give an empirical account of the behavior of this periodically driven damped pendulum. Let's first look at the small forcing limit. What I'm presenting now is what was conventionally presented in a physics classical mechanics course 40 or 50 years ago, which is what I took myself. First point is that if the forcing is really, really small, gamma much less than 1, then we start with our equation of motion phi double dot plus 2 beta phi dot plus omega naught squared sine phi is equal to omega naught squared gamma cosine omega t. And in the small forcing limit, we're barely tickling the pendulum, and so the angle is close to vertical, phi is close to 0, and so in this limit we replace this by approximately equal to phi. In this limit, gamma much, much less than 1, we find that there's periodic motion when phi much, much less than 1. So for small forcing, we make the small angle approximation, we plug it into the equation, it now becomes a linear differential equation. We can solve it analytically, and the solution is periodic motion. So the point is that when gamma is much less than 1, the linear approximation is okay. However, when gamma is less than but getting close to 1, if you then look numerically, you'll see that there's nearly periodic motion. So first of all, there's nearly periodic motion, and when you crank up the driving force, then phi is not that small. And in the spirit of like the good old days of studying deviations from linear systems, one tries to make a perturbation about the linear limit. So the conventional thing was to try sine of phi. So for the small angle approximation was phi, and then you take the next approximation, phi cubed over 6. And if you plug that into the equation of motion, you get phi double dot plus 2 beta phi dot plus omega naught squared, and then you have phi minus phi cubed over 6 is equal to omega naught squared gamma cosine omega t. So what to do then? Well, if we try a periodic solution, that is that if we try phi is equal to some amplitude cosine omega t minus delta. If we plug it into the equation, the presence of the cubic term will give us a cosine cubed term, and the cosine cubed term can be resolved by trigonometric identities as something that involves cosine of omega t and cosine of 3 omega t. So the point is that we find, in fact, that this form of the solution was inadequate, and the solution actually has the form a cosine omega t minus delta plus b cosine 3 omega t minus delta. So when we have a periodic driving force, and the force is a little bit larger than infinitesimal, then there is both periodic response at the same frequency as the drive and 3 times the frequency as the drive. And in this approximation, b will be less than a. So more generally, if we push this even further, keep higher order terms, we would get an infinite series of higher harmonics. Phi would be equal to a sum of harmonic responses. But this really misses the point of what's going on, because if you write the solution as the form of an infinite series, one loses any attempt to be able to understand analytically what's going on. So this picture of writing phi as a harmonic series is really not the right way to approach the problem. But because of the complexity of the problem, we really are only left with looking at the problem numerically.